Good afternoon, everyone. Let's start. So now we are in the topic of adders. We have learned several types of fast adders, including carry bypass adder, the carry select adder, and carry look ahead adder. These are binary adders. And they are adders based on other number systems for fast operation. And we have learned one of them, which is the adder based on the remainder number system, which has limited carry propagation problem. See, there is a message. Let me see on it soon. Let me see what it is. No, I don't see it. The chat. Anyway, let's continue. So today we are going to learn the last type of fast adder in this course. It's called carry-free adder based on a number system called the redundant number systems. In this redundant number system, we do not have the problem of carry propagation. First, let me explain the concept of the redundant number system in decimal format. Consider we are adding this decimal numbers, each of 6 digits is decimal numbers. So the maximum value of a digit is 9. So if we add 2 9s together, the maximum outcome, the maximum sum we can get is 18. So if we code a digit using 2 decimal digits, 2 decimal places, then we don't have the carrier propagation problem. The carrier won't propagate. Okay, so when you add 2 decimal numbers, we don't have this propagation problem. But things will be a little bit more complex when we consider addition of another number. Say, after this addition, we get this number. Now we're going to, so we get this 11, 9, 17, this number. It can be coded in a certain way, so in this way. So 2 digits for one, 2 places for 1 digit. Now say we continue to add a second number, 6, 12, 9, 10, 8, 18. Now this time overall could happen. Say 18 plus 18, we get 36. But this problem can be solved by using a transfer digit, which is similar to carry, but this one doesn't propagate. So we have 36 for this first digit, but we can represent it as 16 plus a transfer digit in the higher position. A transfer digit of 2 in a higher position. Basically, it's 20 plus 16. This 2 is in a higher position, so it has a weight of 10. This is represented in this way. And this 20 is also overflows. So we can represent it as 10 plus 10. 10 is kept in this current position, and 1 is transferred to a higher position. It's something similar to the carry. However, here the carry does not propagate. And that's the key advantage. Yeah. So here you 2, you add it to anything, it won't overflow. I mean, you add it to any legitimate numbers in this position. The maximum here will be 16. So say is 18 plus 18 is maximum number is 36. 36, then you can decompose it into 16 plus 20. So 16 is the maximum value. When you add 2, it equals to 18. So overall, overflow won't happen. With this, you can have this transfer digit, and you can keep this process going on. And you can add more numbers without the problem of carry propagation. You know, the carry propagation is the main issue that slows down the add operation. Now, with this number system, the carrier propagation problem is avoided at the cost of more hardware. We need more hardware to store each digit. So this is the concept in the decimal format. Now let's consider binary format, binary number. Okay, so here we use a digit set of 0, 1, 2 to represent a digit. 0, 1, 2. Now let's consider this normal addition of 2 binary numbers. So 1 plus 0 is 1. 1 plus 1 is 2. Now 2 is within the coding system, within a range that can be coded for a position. So we keep 2 here. So this carry won't propagate. The first time of addition, there won't be any carry propagation issue at all, because 1 plus 1 is 2, and 2 for 2 we don't need to propagate. We can code it for this position. Now let's consider another addition. So we add this sum with another binary number. Or this 1 plus 1 is 2 is okay. For this position, 2 plus 1, then it will overflow. It equals to 3. 3 cannot be represented by this digit set, overflows. The solution is to have a transfer digit. So we represent 3 as 1, 1. 1, 1. So a 1 is in a higher bit location. So 1, 1. Okay, with this, we have a transfer digit. However, this transfer digit won't propagate. It won't propagate all the way through the positions. So when we do this, say for example here, we have 1 here, 1 plus 0 is 1. This won't produce another carry signal. And we can keep doing this additions. And say if after a long process of additions, you get a final number, then you can convert this final number into a normal binary number. Okay, let's take a look at the hardware implementation. This is very efficient. So for binary, for the binary carry-free system, so for each digit, we use actually we use for each digit set. It can be called as, we use 2 bits to represent. It can be 0, 0. The 0 is represented by 0, 0. 1 can be represented by either 0, 1 or 1, 0. Either one is okay. 2 is represented by 1, 1. So now we need to have say 2 registers to recall 1 bit. That's the cost here. We pay for more hardware. I mean, we use more hardware for higher speed. So for each bit of addition in this redundant number system, it consists of this circuit. This is just a normal full adder, 1 bit full adder. It has 3 inputs, including the carry in. So this this is the transfer digit from the previous from the lower bit. Transfer digit from let me see. Well, here we have 2 bits to represent the value of this one, and this is the addition of addition. Is the bit the bit of the number that you are going to add, and this is from the transfer digit from the lower bit operation. And the carry output goes to the next stage, to the higher bit. So the output is here. We use 2 bits to represent this bit set. It's either 0, 1, or 2. So it's hardware is quite efficient, only a full adder, but we needed to use a digit set, a 2-bit digit set to represent each bit. So in the end, it may be necessary to convert the result to form normal binary number by using conventional adder. But this is only done in the final operation after a series of accumulations. So that's the carry-free adder by using some redundant hardware. Any questions? If no, let's move on. So data processing can be carried in a number of manners. Here, it can be in parallel manner, serial manner, or pipelining manner. Parallel is the normal realization. Operations are performed on the whole data world. A serial operation refers to the case that data was processed bit by bit. And pipelining is to divide up the whole process into sub-operations. and to use registers to store the intermediate outputs. And the operation will become clear when we see some examples. The parallel and serial here, let me use this simple example to illustrate. For the ripple carry adder, the normal one we've seen before is parallel because we have an full bit, 1 bit full adder for all the positions. They operate in parallel. Although the higher bit needs to wait for the carry out of lower bits. But there is no flip-flop involved, no store. These are all combinational components. Now for serial, we can use 1 bit full adder and use the flip-flop, D-type flip-flop to store the carry out. So this circuit, serial one, it performs the addition of 1 bit per clock cycle. So it only needs 1 full adder and a flip-flop. No matter how long the bit word is, so however small, however it takes several clock cycles, take n clock cycles to complete an addition. A pipeline is something in between. It has the pipelining circuit has the latency of serial circuit, but it has the throughput of the parallel circuit. So pipelining can be used to speed up the throughput of the operation by breaking the whole operation into some smaller sub operations. The results of the sub operation is saved in registers, and another sub operation is then executed in the next clock cycle. It's like a pipeline in the manufacturing line. In each position, you perform a small task. And different positions perform different tasks. So the speed or the throughput will be high, but still it takes. So for every operation, it needs to go through the first from the first sub operation to the final sub operation. So the latency is still there, but the throughput is high. Let's consider a pipeline adder. The direct implementation of pipeline adder is shown here. 2-stage pipeline adder is shown here. Now, say we divide each input words into 2 subgroups, the LSB groups and the MSB groups. So the LSB groups are added by a sub-adder. And then its carry output is stored by a register. And for the MSBs, we use a register to store its value. So when the output of the LSB carrier, the carry output of the LSB is available, then we perform the addition of MSBs. So when the MSB sub-operation, a sub-addition is performed, then the LSB can accept inputs of next clock cycle. Say if let's consider time n. So when MSB is perform the this subadder is perform the MSB addition for the data with time index n, and this one it can accept data input with time index n+1. It's already working on the next sample. That's called pipelining. This direct implementation of pipeline adder requires 4 registers. So register for the MSB of the 2 inputs, and register to store the value of carry output, and also register to store the LSB's sum output in order to align with the MSB's sum output. So 4 registers are required. 4 groups of registers are required, and it can be rearranged to save some register needs. Say we do this. The LSB and MSB additions, sub-operations are performed simultaneously. Then the outputs are stored in these registers. This is the carry output of the LSB adder. Then this MSB adder, this another adder is used to perform the addition of this value and this carry output value. So when this third deploy is operating on some data, the first stage is working on the next sample. This is a pipeline operation. So any questions regarding this pipeline concept? If no, let's check some Verilog implementation example. So this code implements this pipeline adders. So we define a module called add1p, p for a pipeline. Some parameters here. Width is the input words width. We have A and B 2 words. Each is 31 bit long. And then we divide it into 2 subgroups. With the LSB group has a width of 15. The MSB group has a width of 16. Now, input signal X and Y, each is a binary number of widths. It has a width of width, this parameter. So it's from width -1 to 0. So width is width. The sum is output. This variable sum denotes the output, same width as the inputs. So and clock input here, so 1 bit signal, and there is a test port to observe. The test port is to observe the carry output of the LSB sum operation. Here we need some registers to define some registers. L1, L2, and sum 1. They have the width of LSB group. And R1 R1 has one more bit wider than the LSB group. Starts from width 1, not width 1 minus 1, has one more bit. And for register variables, register type of variables, and with the width of width 2 for the MSB groups. Now we have a always block here. So at the rising edge of the cross signal, we do the following procedure, included from this begin to end. So this always, remember, this always its operation is like this. First, when it sees the rising edge, and all the right-hand side of the statements within this block are read. The program, the simulation program, read the right-hand side values at that instant. All the right-hand side statements, variables, are read at that instant. Then do the assignment. So read first at that moment, regardless of the change. So read at that instant, then do the assignment. Okay. Now let's see. So the LSB of input X is stored in register L1. The LSB of input Y is stored in variable in register variable L2. The MSB are stored temporarily in register L3, and MSB of Y is stored in L4. This actually this step can be omitted to save registers, but for the sake of clearness, here we do this. We use this registers to store the MSB and LSB of input X and Y. Now, let's here these two lines. This line implements this function, this block. The LSB of X and Y are added to form the content for R1, register R1. Because R1 needs to take care of, I mean, the sum of the two binary numbers should have one more bit than the inputs. So R1 is the L1 and L2 sum, but we append a 0 at the MSB position of these two numbers, because the MSB of these L1 and L2 could be both 1. Then 1 plus 1 it gives a carrier. So R1 here, you see this R1 here has one more bit than the LSB groups. So R1 contains the sum output of the LSB as well as the carrier output of this sub operation. And then MSB is a value which is has been stored in L3 and L4. They are added and stored in internal register R2. Okay, so that's the first stage of the pipeline. And then the second stage of pipeline is implemented here. So the R1's content except the MSB is stored in register S1. So R1's content is read at the rising clock edge. Now be careful. This is the old content of R1, not the updated content of R1. Right? At the rising edge of the clock, all the right-hand side of the statements are read simultaneously. So this R1 is the R1 of a previous clock cycle, right? It's not this updated R1's value. This is important because it tells the pipeline operation. Okay, so the R1's content before update is stored in S1, and R2 we perform the summation. Perform the summation of R2 plus the carrier in. Carrier in R2 is here. Carrier in is the MS bit of R1. So R2 plus R1. So assigned to S2. Again, this R2 and the R1 are the content of these two registers before they are updated, just at the rising edge of the clock cycle, before this update assignment. So these contents are one clock cycle older. The content here in R1 and R1 here and R1 here are one clock cycle earlier than the content of R1 and R2 here. And that forms the pipelining time sequence. Okay, so that's the main part of this pipeline adder. Then here, outside of this always block, we assign this carrier, R1's MSB position into an output port in order to observe it. This is just for test port, just to observe this internal signal. And then we concatenate S2 and S1. Concatenate S2 and S1 to form the sum output. Okay, so that's a two-stage pipeline adder. There's a question on the chat, but somehow I could not see it. I don't see the chat box at all. Oh, okay. Oh, it goes to this screen. Can we use this one instead of this two? -1, we're getting register size of I3 and I4. But if for this specific example, you say width 1 is 31, width is 31, width 1 is 15, width 2 is 16, you can do that. But that is not general. That's too specific. I mean, only. Well, it's okay as long as the algebra is correct. You can do that, but it's not intuitive. Okay, let me close this chat. Okay, closed. This is another example of a pipeline. Here we have 3 pipeline stages, 3 pipeline sequence. A similar construct. Say so the total width is of input words is 28 bits, and we divide into 3 groups. Else, say group 1 is 9 bits, second is 9 bits, and finally we have 10 bits. An intermediate word 18 bits. Some intermediate, well, it's 18 bits is the sum of this with 1 and with 2. For input x and y of width. The sum is same as the width of x and y. Output we have the so this LSB carrier, MSB carrier, there are some observation point, test port. And okay, so these are test ports and input clock here. Define some register variables which will be used in this block. Now we have this always block at the rising edge of clock with the following block. First, we split the input words into 3 groups. This is the L1, L2 stores the LSBs of x and y. L3 and L4 stores the middle bits of the 2 inputs. L5 and L6 stores the MSBs of the 2 inputs. Now, the first stage of the adder, this Q1 is the intermediate value. It should be 1 bit wider than L1 and L2. So we concatenate this LSBs with 1, with 0 on the MSB. So this is an addition of the sum of the LSBs. And this is sum of Q2 stores the sum of middle bits. Q3 stores the sum of MS bits. These are intermediate sums. They don't consider the carry in. The MSB and middle bit summation. They don't consider carry in yet. Carry in will consider next. Then the second stage. So V1 stores the content of Q1 without the MSB. The MSB of Q1 is the carry out. Again, this Q1 is 1 clock cycle earlier than the Q1's content here. This Q1 is before the update. Q1 in this line and Q1 in this line are different. And this Q1 is the Q1's value at this instant, E value at this instant at the rising out. This Q1 is the value after E value after the update. they are one clock cycle difference in time. V2 stores the middle bit content, except the MSB. I'm sorry, let me make a correction. It's not this. V2 stores the summation of the middle bit and carry out of LSB. This is the middle bit of Q2 here before update, and Q1's carry out, and Q1's MSB is carry out. And third statement is Q3's value before the update plus Q2's MSB and carry out before the update assigned to V3. That's the second stage, second pipeline stage. Okay, now here comes the third stage. So V1's value is assigned to the sum S1 this register. It will be the output of this. It will be the sum output LSB. So again, here V1 is evaluated before it has changed its content. It's evaluated at the rising edge of the clock. So this V1 is different from this V1. So this V1 is one clock cycle earlier than V1 here. That's the pipeline requirement. V2 content is saved in S2. But now the last group, MSB group, needs to add V3 with the carrier output of the middle bit. This V2 is carry out. V2 is the middle bit output, and the MSB is the carry out. Okay, that finishes this block. We have 3 pipeline stages. The last stage is 2 clock cycle later than the first stage. And we need some intermediate registers to store the content. We need those registers. Otherwise, the data will be overwritten in this pipeline process. Here outside the block, we have this assignment statement to assign this wire Q1's MSB to this output port for observation, and same for this one. And finally, we concatenate S3, S2, and S1. We combine them into the sum output of the addition result. Okay, so that's a pipeline idea. The key thing here is to use register variables to store intermediate results. Without this temporary registers, pipeline operation cannot be performed because the new data will overwrite the old data. But with this intermediate registers, so we can do this subtask independently without the influence of new inputs. Okay, I think I will stop you here. So. Any questions? If no, see you tomorrow. Okay.